Hello and welcome, everyone. In today's lecture, we are going to dive into a really important topic in the world of data, especially as we deal with massive distributed systems. We'll be talking about transaction processing and consistency models. These concepts are fundamental to understanding how modern databases, both SQL and NoSQL, work under the hood. So let's get started. So, what exactly is a transaction? You might think of a financial transaction, like buying something with a credit card, and that's actually a great way to start thinking about it. In database terms, a transaction is simply a sequence of actions. It's a single logical unit of work. These actions can involve reading data from the database or writing data to the database. Think about booking a flight online. This single booking action might involve several smaller steps: checking for available seats, reserving a seat for you, processing your payment, and finally issuing your ticket. All of these steps together form one transaction. This can be any combination of what we call CRUD operations: create, read, update, and delete. A transaction bundles these operations together so they are treated as one single event. Now, when we talk about transactions, especially in the world of traditional relational databases like SQL, there's a famous acronym you absolutely need to know: ACID. ACID is a set of four properties that guarantee our transactions are processed reliably. It's like a promise that the database makes to ensure our data stays valid and correct, even if things go wrong, like a power failure or a network error. Let's break it down. First, A stands for atomicity. This means a transaction is atomic. It's an all or nothing deal. The entire sequence of operations within a transaction must be completed successfully. If even one part of it fails, the entire transaction is rolled back, and the database returns to the state it was in before we started. Think of a bank transfer. You want the money to be withdrawn from one account and deposited into another. You don't want it to only do half the job. That's atomicity. Next, C is for consistency. This ensures that any transaction will bring the database from one valid state to another. The database has certain rules, like an account balance cannot be negative. A consistent transaction will never break these rules. If a transaction would violate the database's rules, it will be rolled back. I stands for isolation. This is a crucial one. Isolation means that multiple transactions occurring at the same time should not interfere with each other. It's as if each transaction is running in its own isolated bubble. The result should be the same as if the transactions were executed one after another, sequentially. We'll see why this is so important in a moment. Finally, D is for durability. This property guarantees that once a transaction has been successfully completed or committed, all of the changes it made to the database are permanent. They will survive any subsequent system failure, like a crash or power outage. When the system comes back online, your data will be there. Okay, so we've just talked about the four ACID properties. Now we're going to take a much deeper look into one of them: consistency. This concept becomes especially interesting and a bit more complex when we move from single, centralized databases to the large distributed systems common in NoSQL. One of the biggest mindset shifts when moving from a traditional, centralized relational database to a modern, cluster-oriented NoSQL database is this idea of consistency. Relational databases, which are built on the ACID model, put a very strong emphasis on what we call strong consistency. This means that after you write a piece of data, any future read operation from anywhere will instantly see that new value. It's simple and predictable. But in the world of NoSQL, where data might be copied and stored across many different servers around the world, achieving that level of immediate, strong consistency can be slow and difficult. So NoSQL databases introduce a wider spectrum of consistency models. We start to consider various different forms and degrees of consistency, which gives us more flexibility.
Let's look at a practical example to understand why this can be tricky. Imagine a hotel booking system with its database distributed across servers in Mumbai, London, and Boston. On the screen, we see three people: Pramod, Martin, and Cindy. Here's the scenario. Pramod, who is connected to the Mumbai server, books the very last available hotel room. The Mumbai database is updated immediately. However, this update takes some time to travel across the network to the other servers. Let's say the update has not yet reached the London server. Now, Martin, connected to the London server, checks for rooms. Because his server hasn't received the update yet, he sees the room as still available. At the same time, maybe the update has reached the Boston server. So when Cindy, who is connected to Boston, checks, she correctly sees the room as booked. This situation, where different users see different data at the same time, is what we call inconsistent reads. It's a classic example of a read-write conflict. This diagram illustrates the challenges we face with consistency in distributed systems. We have to manage update consistency to prevent two people from updating the same data at once, and replication consistency to make sure all copies of the data eventually match up. So to handle these challenges, system designers have come up with several models. Let's go through them. The most common model in many large-scale systems is eventual consistency. This model accepts that there will be temporary inconsistencies between different replicas or nodes, but it makes a promise. If no new updates are made to a specific piece of data, eventually all nodes will be updated and everyone will see the same value. The period of time during which this inconsistency exists is called the inconsistency window. During this window, different people might see different things. For example, you might post a message on a social media app. You then immediately refresh your feed, but your request goes to a different server that hasn't received your post yet. It might look like your post was lost, but it's just delayed by the inconsistency window. To solve that specific problem, we have read-your-write consistency. This is a very user-friendly guarantee. It means that once you have made an update, anytime you try to read that data again, you are guaranteed to see your own update. A similar idea is session consistency. This provides read-your-writes consistency, but only within a single user session. If you log out and log back in or switch to a different device, you might lose that guarantee. Finally, there's user-perceived consistency. This is less of a technical model and more of a business consideration. It's about how long a user expects to wait to see an update. For a bank transfer, you expect it to be instant. For a like on a photo, a few seconds of delay is probably acceptable. So we can think about consistency as a spectrum. On one end, we have strong consistency. This is the ACID model. After an update is complete, any subsequent access by anyone, anywhere will return that new updated value. It's strict and immediate. On the complete opposite end, we have weak consistency. Here, the system doesn't guarantee that you'll see the updated value right away. You might have to wait or meet certain conditions. And in the middle, we have eventual consistency. As we discussed, the system guarantees that if no new updates are made, eventually all reads will return the last updated value. The most important takeaway from this slide is that there is no single best model. The right choice always depends on the needs of the application. Does your application absolutely require every user to see the exact same data at the exact same time? Or can it tolerate a small delay for the sake of better performance and availability? Okay, so we've seen the strict guarantee everything world of ACID. Now let's look at the alternative philosophy that powers many of the NoSQL databases you'll encounter. This model is called BASE.
BASE is another acronym, and it stands for Basically Available, Soft State, and Eventual Consistency. It represents a completely different set of priorities compared to ACID. First, basically available. This means the system guarantees availability. It will always respond to a request. It might not give you the most up-to-the-second consistent data, but it won't give you an error. It prioritizes being online over being perfectly consistent. Next, soft state. This indicates that the state of the system can change over time, even without any new input from a user. Why? Because of the eventual consistency model. Data might be changing in the background as the different nodes are synchronizing with each other. In this model, data consistency becomes the responsibility of the application developer, not the database itself. And finally, eventual consistency. We've already covered this, but it's the core of the base philosophy. It accepts that data will be inconsistent for a period of time, but it will converge to a consistent state in the future. It's a delayed consistency as opposed to the immediate consistency of ACID. So, to summarize the base model, a base data store values availability above all else because availability is critical for scaling to millions of users. The trade-off is that it does not offer a guarantee of consistency at the moment you write the data. Overall, the base model provides a less strict, more flexible set of assurances than ACID. The core promise is that your data will become consistent at some point in the future. This approach allows for much higher performance and fault tolerance in large distributed systems, which is why it's so popular for web-scale applications.